Yeah.
In that they had some people that had a large response during the run-in period and should have been dropped and they didn't drop them. Like, so I didn't know if that was the answer.
Yeah. So it's not, don't stress too much about like it was proper randomization used or things like that. It's just kind of, I guess, when you read a study, I think in our class it's very easy to just say like, oh, here we have some data and we got it from a random sample and things like that. But in real life, the practical application of trying to control randomization and things like that, it's actually very difficult, especially when you're dealing with a group of people that, you're not dealing with the general population. Well, no matter what you're trying to do, it's hard. Okay, so I just kind of want to talk about a few of these things. All right. So blah blah blah. We have all of this stuff, and they try to show you how they broke up all of their participants and stuff, and so it's all of this, and so we get this table, right? And recently these types of tables have been come under some criticism, but basically. The point of this table was to show that after the randomization, the two groups were quite similar. That, according to the baseline statistics, the two groups are similar, and that we're not trying we can't say that the different outcomes are due to the fact that one group, made lots of money and the other group didn't make money or something like that. Okay, so they check all of these different things that could be associated with the results, and they don't, the point of this was to kind of show that the two groups are fairly similar. Yeah.
Why are the tables coming under criticism?
Because basically it's like if you've done randomization, then it doesn't really matter, I guess. Yeah, but that's kind of the point there. Okay, so let's talk about this table. This is the table of results, really, that really I would say is the one that matters. Okay, and then so we get kind of funny things here. Okay, so we get we have a p-value of 0.34 at baseline. And what this means is that the question is the mean of 11.8, is that significantly different from the mean of 10.3? When you perform a t-test to compare these two means, is mu1 equal to mu2, the p-value ends up being 0.34, to say that at baseline, there is not a significant difference between the baseline hyperactivity measure. Okay, and for inattentiveness, is 15.6 different from 15.8? You get a p-value of 0.87, not significantly different. Okay. So if we look at this total thing, okay, at baseline 25.9 versus 27.6, we get a p-value of 0.32, not significantly different. Negative 5.2 versus negative 4.4, again, the p-value there is 0.76. So the difference between baseline to week 8, the difference between the placebo and the hypericum group, or whatever, the treatment group, is not significantly different. Okay. On the other hand, if we look at the confidence interval, what do we see? The confidence interval for difference baseline to week 8, this is entirely negative, and this is also entirely negative. Okay, and we said, if 0 is not in the interval, you have evidence of a significant difference here. So what's going on? This is to say that the change from 25.9 to 20.7, which is a change of 5.2, 0 is not in this interval, so there is a significant difference from baseline to week 8. Okay, so under the placebo group, there is a significant difference from baseline to week 8, and under the treatment group, 27.6 to 23.2, 0 is not in that interval, so there is also a significant difference from baseline to week 8 in the treatment group. Okay, so this is to say that both placebo and the treatment seemed to make a difference between baseline to week 8, okay? That appears in the confidence interval. On the other hand, the p-value of 0.76 shows that there is not a significant difference between the overall effect of placebo versus the treatment group.
Are we comparing that p-values with alpha? Like, wasn't there alpha 0.05?
Yeah, so if alpha is 0.05, huh?
No, go ahead.
So if the alpha is 0.05, we would say we don't have evidence that there's a difference between the effect due to placebo and the effect due to treatment, okay? But on the other hand, if we ask the question, is there evidence that there is an effect? The answer is yes, because this is entirely negative. 0 is outside of the interval, so we do have evidence that there is an effect. Yeah?
Just looking at this data, could you argue that perhaps there was an effect because we can see that there's no 0 in that confidence interval? However, since we have a very large p-value in that difference, that perhaps the placebo and treatment are independent to what actually happened in the study, or not in the study, but in real life. It sounds to me, at least what I'm seeing, is that there was some sort of other factor that helped these ADHD kids, and it wasn't due to placebo or the medication or the treatment. It just happens to be that there was a significant difference, but it has nothing to do with the medication. That's what it looks like to me.
Wait, so I'm sorry, I'm not 100% sure what exactly.
So in other words, I see that there's no 0 in between in the confidence interval.
Correct.
Which means that there was a significant change.
From baseline to week 8.
Right.
Yes.
However, the difference between the placebo and the treatment
Yes.
is insignificant.
Correct.
So that means that there was something else that was helping these kids,
and we, yeah.
Nor the treatment that we can glean from this.
So I would argue that we see an improvement from baseline to week 8 because of the quote placebo effect, meaning that the placebo effect, which is like the mechanism of how it works, is not well understood, but we know that this thing exists. That if you give somebody some meds, whether it actually, or you give them something, whether it should do something or not, somehow it affects the results. Okay, so we see that there is something because from baseline to week 8, their scores improved. Okay, so that seems like it's for real. But then if we compare, was the actual, hypericum perforatum, is that different from placebo? The p-value there says no, and so yeah, yes.
Is it at all meaningful that the St. John's wort group actually improved by less than the placebo group? Like if your placebo than your treatment? Or is it close enough that it's like, oh, what is that?
Yeah, so you could argue that, right? You could say like, well, if anything, it seems like the placebo is even more effective than St. John's wort or something like that. We could say that, but the p-value there is so large that it's I would say that even if anything, it appears that way, but according to the statistics, there is not a real difference between these two things. Yeah, but if we had a directional test and we said, is St. John's wort more effective than placebo, we certainly don't have evidence of that. Yeah. Yes.
But another thing regarding what you said, I haven't read the paper yet, but then it could be that over the course of the week, the children, they got better at doing whatever task they were assigned to do, and that might have raised their overall score. That's another thing that could be, right?
I'm sorry?
That could be another thing that contributed to just the overall raise in score.
That they just got better with time anyway?
Yeah.
Yeah, I mean, that's, who knows, right? I have some doubts on this, that just in 8 weeks, like, we don't have, there wasn't like a separate control that just received no placebo either, you know. So we're testing, is this more effective than placebo versus is this more effective than nothing? And you know, if you wanted to see is time a factor there, you would need a group where they just got nothing, where we could kind of extract out the effective time. But here, because we don't have that, we can't really say it is because of time or not. So here, the only comparison is it more effective than placebo? We don't have evidence of that yet.
So we have, oh, sorry. Go ahead.
The difference between the confidence interval and the p-value, there was a part in the book that was talking about the definition of significance. This is an example of that then, correct? Where it says there is a difference, but it's not significant enough to...
Well, there's two different comparisons here going on, okay? The p-value compares St. John's wort to placebo. That's what the p-value is associated with. The confidence interval here is baseline to week 8. Okay, so they're looking at different things. Okay, so the fact that 0 is not in the confidence interval shows that baseline to week 8 is different from 0. The fact that this p-value is 0.76 shows that there is not a statistically significant difference between negative 4.4 and negative 5.2. Okay, and so you know, sometimes when you read research articles, they'll have tables published, and you know, whenever you're the researcher and you make a table, it always makes sense to you. But when you're the reader, you look at a table and you're just like, I'm not quite sure what this table is talking about. So yeah, you know, so I've noticed in the past, if I didn't explain the table, students often had the wrong interpretation about what these confidence intervals and p-values mean in the table. So I want to kind of point that out. Yeah. Let's see what other. So the adverse effects. Yeah, was there a difference between? So you know, we do get a significant difference between the adverse effects. You know, 15 people had adverse effect. You know, had rashes under placebo, whereas no one had rashes under St. John's wort. And so you know, we don't quite understand that, but that, you know, that is a significant difference there, and things like that, and something like that, right? So, and then when you get the same number 4 to 4, your p-value is basically 1, right? So you know, who knows what this is, but yeah, okay. And then we have all of this. You know, is there a difference? And so this is all of this other stuff that may or may not be related or of importance. Okay, but that was that. You know, I had in previous classes or previous quarters, I had a lab for ANOVA, but I guess the students thought the article was boring or something, because it was hard to find an article that had Oneway ANOVA, and it was on smoking initiation age, and I don't know. It was all right, I guess. But, okay, let's talk about some of these other forms of ANOVA and certain things. So we do have, there are conditions for using ANOVA. Okay, so conditions for using ANOVA. Okay, so one is basically random and independent. Okay, so we have the samples should be randomly selected from their population, or at least it must be reasonable to think that they have been randomly selected from the population. Okay, because in real life it's very difficult to get a truly random sample, but if you can say, you know, I have no reason to believe that these individuals are not a random sample, then that's fine, okay? and then the different groups must be independent of each other. Okay, so the okay, and then this other condition, this is a little bit tough. It must be like there's a strong assumption, and we are assuming that the population standard deviations are equal to each other. Okay, and that's or at least are comparable to each other. Okay, so we're assuming that the population standard deviations are equal to each other, or at least comparable. Okay, and so if in your data you get one group with way more spread than the other groups, or one group with much less spread than the other groups, there could be some problems in the analysis. I mean, it's just formulas, and so the computer will spit out a result, but those results may not be completely reliable. Okay, and this is just a problem that it's hard to do anything about. Okay, it's hard to yeah. Question.
Would the error in accuracy be like proportional to how like the difference between the standard deviations of populations, or is it just random? It's just not.
I'm sorry. What the error in accuracy of
the results from them on the computer? If the standard deviations of populations are not equal or comparable, is it roughly proportional to that like difference, or just not accurate at all?
Yeah, it's hard to kind of answer this. Yeah, basically, at some level, you have to just say it doesn't work. But you know, statistics is a little bit of a messy subject because you're dealing with data that we don't know the population is the thing, and so we kind of have to just put assumptions on the population, and sometimes the assumptions work out, and that's great. Sometimes the assumptions aren't correct, but you get lucky and it works out, and then sometimes the assumptions are wrong and you don't know it and you make the wrong conclusion and everything comes out terrible. But it just it's hard to say. So basically, because there's like mathematical principles underlying these tests, right? And so these mathematical principles are counting on the fact that these assumptions are true. And if those assumptions are not true, then the results from the mathematical principles just aren't going to work. But because data is messy, sometimes we get lucky in this stuff. So I can't really say that the amount of accuracy, it's just going to be wrong. But you know, you do have a little bit of wiggle room because, you know, maybe this population has this much spread and this other population has this much spread. Maybe that's fine, okay? But then maybe like from this much to this much, that's no good. Yeah, you do get a little bit of wiggle room, but it's hard to say. Yeah.
Is that because then you're just one is just going to fit right into the other or something? That's a possibility? Or?
So the part comes in is that we're talking about the total variance, right? The total variance of the group, and we're trying to split out the total variance of the group into two parts, okay? And so if if you have different amounts of variance between in one group and another group, then the total variance that exists, it's hard to say this amount of variance is because of this this group and that group, right? So when you talk about the total variance, there's kind of this assumption that all of the groups have about the same amount of spread within itself, which may or may not be reasonable. Okay, so and and if you have smaller-ish samples, it's hard to say if it's truly different or not. So anyway, everything's a little bit messy, and there's kind of this quote about statistics that all statistical models are wrong, but some of them are useful. Okay, and so really, you're not going to have the perfect model that works all the way, but it might be like just a tiny bit wrong that it's still useful. Okay. Okay, let's talk about some of the other designs that we have. Okay, so we had with Oneway ANOVA. Basically, we said each individual comes from a grand mean plus a group mean plus a residual, right? So we have grand mean. I'm sorry, group effect and a residual. Okay, that's Oneway ANOVA. We're just saying we have different groups because of different group effects. Okay. We have something called the one-way randomized block design. Okay, and so in this case, we expect basically I'll write it and I'll say an individual value is a grand mean plus a group mean plus what we call a group effect plus a block effect plus a residual. So that we have grand mean, group effect, bless you, block effect, and a residual. Okay, so what is a block effect? Okay, so here we have things that could affect the outcome, the response that we're looking at. Okay, and perhaps this is something that we know affects our data, but we can't really get rid of the fact that this thing exists. Okay, and so so let me kind of draw a little picture here. Okay, so let's say we want to know, like, so this is a plant, and we want to know, like, how much will it grow? All right, and what we want to test is, like, what if we just give it water versus like some kind of fertilizer, and maybe we have like different types of things, the nutrient stuff that we can give the plant to help it grow, right? So like what will, so we've got like control will just be water, and then treatment 1 is fertilizer brand A, and then treatment 2, maybe fertilizer brand B or something like that. And so we want to know, like, what affects how much the plant grows. All right, so we're going to look at plant growth. Okay, and so let's say you your lab where you're going to conduct this has a window. Okay, and so this is an overhead view of our lab. Okay, and then, so let's say there's a window here, and you want to know, like, which of these things is going to work out the best. Okay, but because of the way the room is, maybe this area gets the most sun. This gets some sun, and this gets the least amount of sun. Okay. And so a terrible design, like I don't know how many plants we want. A terrible design would be to put all of the fertilizer B in this group, and then fertilizer A here, and then the control group over here, right? Because at the end of our experiment, if we see that fertilizer B grows the most and the control group grows the least, we don't know if it's because fertilizer B is the most effective or because they got the most amount of sun, right? So this would be a bad design. Okay. If we did a truly random design, if we just randomized everything, it's quite possible that we still end up getting a bunch of B plants in the most sun and still get a bunch of control plants in the least sun group if we just did truly random. Okay, and so we have basically the random block design, where what we will do is we're going to randomly make sure that in the most sun we get 2 from group B, 2 from group A, and 2 from group control. Okay, and over here we also get 2 from B, and 2 from A, and 2 from the control. Okay, and over here, you know, again, 2B, 2A, and 2 control. All right, and so each one will have 2A, 2B, and 2C. Okay. A, 2B, and 2C. So this will be the randomized block design. Okay, and so in our analysis, we're going to say, yes, we are aware of the fact that some plants got more sunlight than others. Okay, and so when we set up our experiment, we made sure that in each zone, we had 2 from A, 2 from B, and 2 from C, so that if across, if in all 3 regions, right, if in the least sun, the some sun, and the most sun, fertilizer B grew the most in this region, fertilizer B grew the most in this region, and fertilizer B grew the most in this region, we can confidently say that fertilizer B is the most effective, okay? And so, because we can parse out the effect due to the sunlight, okay? Because we are aware that sunlight affects plant growth, okay, or we at least expect that, and so we would take that into account into our design so that we can say, yes, at the end of our experiment, we see that B grew the most in all 3 zones of the room. Therefore, fertilizer B is the most effective in increasing plant growth. Okay, so my experiment. You know, B grew most in all 3 regions. And then B is the most effective. Okay, and so that would be the one-way randomized block design. Okay, and then And your ANOVA table would have, as far as the sources go, you would have source due to group, source due to block, and source due to residuals. Okay, and you would have sum of squares due to each of those, and mean squares, and F ratios, and things like that. Okay, but we're not going to bother with this kind of trying to calculate this by hand. Okay, but this analysis does exist. Okay, and so that's the one-way randomized block design. We also have what we would call a two-way factorial design. Okay, and so here it looks quite similar. We would have each individual value is because of a grand mean plus you know, and the symbols might change from textbook to textbook, but I'll just use the ones that our textbook uses. And so this is our, we'll call this treatment, or I'm sorry, factor 1 effect, factor 1 effect. This is factor 2, and this is called the interaction. Interaction, 1R? Okay. And then we still have the residuals. Okay. There will always be a residual because individuals are different from one another, so you can't get rid of that. That always will exist. Okay. So, you know, it just seems like we're just adding something else here. And we are. So before, and perhaps we could use this, but here we're just saying like, oh, sunlight we know affects stuff, and so we're going to include that in our analysis as the block effect. Okay. Over here, we are saying, you know, we've got two different factors. So, you know, it's like before it was the fertilizer and the sunlight. Here it could be something else, and we're thinking, you know, there could be an interaction between these two factors. Okay, so an example is, let's say we have, you know, we want to know like marketing stuff. Okay, so we're looking at like Y is like our total sales for the month or something like that, sales of product. And then tau could be like, did we advertise on TV? TV advertisements. And then beta could be like radio advertisements or something like that. And then, and so maybe one month you just did TV ads by itself, and you saw something like radio sales went up, or product sales went up like, you know, $1,000 or something like that. Okay. And then another month you did radio ads all by itself, and sales went up $500. Okay. And so if these are the effects, if there's a month where you run both TV ads and radio ads, what we would normally expect is we would expect total sales to rise up $1,500. Okay? So, you know, if we ran both, we might expect a rise, an increase of 1,500. Okay, but maybe to our surprise, it goes up like $2,000 or something like that. You know, maybe there's like this synergistic effect of the TV and the radio, and people are like, oh, I really want to buy. You know, it's just something silly, right? So, you know, perhaps we see a quote-unquote synergy, or maybe an opposite thing where you're getting less less than you expect, okay? Synergy effect and see an increase of 2,000 or something. Okay, so in that case, we would say there's an interaction effect. And this is the Greek letter gamma. Okay. Of, about $500 or something like that. Okay, and so this is just a very simplistic example, but you could have, your two factors somehow working together to produce more, or working against each other, or something like that. And so, so that's taken into account with kind of a two-way factorial design. Okay, and then you can, depending on the thing, you can just add more. You could add a third factor in there, and then you would have interactions between factor 1 and factor 2, interactions between factor 1 and factor 3, interactions between factor 2 and factor 3, and interactions between all factors 1, 2, and 3. Okay, and then and this is called the factorial design, where as you add more and more factors that could go into your thing, your design gets more and more complicated. And effectively, the analysis for ANOVA, the general principle still remains the same. We try to parse out the total amount of variance into, like, what can be attributed to this factor all by itself, what can be attributed to the interaction between these factors, what can be attributed to the interaction between all three or all four factors, and things like that. And to do it by hand would be very tedious, but the computers can do it very quickly for you, and it's not too bad. So we have that. Okay, and so these other methods do exist, and you can kind of skim through these chapters in the book, because I'm not going to be expecting you to have to do this by hand. You should know Oneway ANOVA by hand, but that's about that. Let me think. Is there anything else that I want to say? I think that is it for today. So that's Oneway ANOVA, or just ANOVA in general. Next week we'll talk about linear regression, part of maybe a very widely used tool, and maybe also a widely misused tool in statistics. So that'll be next week. The week after will be a review, and then after that is your final exam. So, okay, that's it. Yeah.